Okay, great. Thank you, Joelle. So let me now move us along, and it's my distinct honor to welcome our colloquium speaker, Sydney Schreppler, back to Berkeley. Unfortunately, we're not physically all back together, but hopefully that'll happen soon. As many of you undoubtedly remember, Sydney was a member of the Berkeley physics community for many years. She joined us in 2010 after finishing her undergrad studies at Yale University. To pursue her doctoral studies at Berkeley. Fortunately for me, her undergrad research advisor, Jack Harris, had said a few kind things about AMO physics, and this gave me a chance to talk to Sydney and recruit her to join my research group. For her PhD, Sydney conducted experiments on quantum optics using an experimental setup where cold atoms are placed inside of a high finesse optical resonator. You can see the picture of that setup behind me here. This setup is generally useful for enhancing the interaction between light and matter, and this allows both for highly sensitive optical measurements and also for both matter-mediated light-light interactions and also light-mediated atom-atom interactions. And all three of these aspects were covered in Sydney's PhD work. Sydney's first great contribution to my lab was serving as a graduate student servo, keeping our optical setup steady on long time scales that were required over the very slow repetition rate of our experiment. She eventually made the setup very much more robust, and this led, for example, to her observing the quantum limits of optical force detection for the first time. But undoubtedly, this manual experience in our lab had a big influence when Sydney decided to leave AMO systems behind and enter into the field of superconducting microwave quantum optics, where things are, as I understand, much more robust. So concepts of her PhD research extended into this new area, but she was able to study very new regimes of quantum optics and also to develop the technologies that will be required for quantum information science. In 2019, she finally moved from Berkeley and took up a position as a quantum hardware engineer. So I'm curious to know what that job title entails. Now within the Microsoft quantum program based up in Redmond. Among Sydney's honors, I'll mention a couple that really stand out to me. One is, you may recall, she was awarded the Lars Cummins Memorial Award for the outstanding experimental physics grad student at UC Berkeley. So that was a wonderful honor. And then as a postdoc, she was also supported by the L'Oreal USA Fellowship for Women in Science. So Sydney, it's lovely to have you back, and I look forward to see what you've been up to.
Thank you so much, Dan. Let me share my screen. I hope it works. Share. Okay.
That's
good. It's good. Wonderful. Thank you. It's really an honor to be virtually back here at Berkeley. And I feel so grateful to Dan and to the department for inviting me for this virtual visit. It gave me an excuse to go back into my photo album and pull out some photos to remind myself of my time both in Dan's ultra cold group and in the QNL lab. And I also have some wonderful memories from the Berkeley Physics Department working both with the COMPASS organization and with SWIPS. And I can't wait until I can visit again in person to see what you all have been up to. Many of us in this call and in the physics community observe quantum effects pretty regularly in our research. But when we start focusing on quantum applications, and the application I'm particularly interested in right now is building quantum computers, it's not enough to just observe quantum effects. We're also interested in manipulating those quantum effects, controlling the interactions and the states for use in computations. And so two early Nobel Prize winning examples of quantum state manipulation are shown here. So these are, I think of them as single quantum objects being manipulated to form a cat state. On the left, you see a single ion that's put in a superposition of two locations in space. And the researchers can control the relative phase of those two states and thereby the phase of the interference pattern measured. And they do the same thing in the group of Aroche with microwave cavity photons that are here put into another Schrödinger cat state. And again, the phase of that state can be controlled. So this is the early experimental demonstrations of quantum object manipulation. We can also manipulate ensembles of single quantum objects forming one massive quantum state. So some of you will be very familiar with the picture on the left of a very large ensemble of cold atoms demonstrating interference because that entire ensemble can be described by a single coherent wave function. And on the right, early experimental evidence of the quantization of flux through superconducting rings. And this is allowed because the Cooper pairs, the many, many Cooper pairs in a superconducting ring can again be described by a single wave function. Now, the next step in demonstrating manipulation of quantum objects on the way to quantum applications is few body interactions, or in the quantum computing community, what we call multi-qubit gates. So here you see taking two ions on the left and allowing them to interact such that the parity of the two ions in the bottom graph is oscillating. And when you can control the phase of that interaction, or alternatively the time of the interaction, you can choose a point such that the atom-atom interaction, the ion-ion interaction, realizes a C0 gate, which is one of the principal components of building a quantum computer. And as a fun example of how this is research that's going on in many different kinds of systems, I'm showing you some work in progress hot off the presses in the QNL lab here at Berkeley, where using very similar interactions to the ions, the group in QNL is plotting the two qubit states of superconducting qubits as a function of time and showing that indeed they entangle those superconducting qubits. And so you can see that entanglement growing with this dashed line here, which is showing concurrence. And as I say, this is just the kind of thing that they're tuning up in the lab every day to build their multi-qubit quantum interactions. So all of those examples I've just shown you now have been cherry-picked for a Berkeley audience because they're examples you should be familiar with based on all the wonderful research going on in the physics department here. And some of them were examples of fermionic quantum states, some of them were examples of bosonic quantum states. But coming as I do now from the Microsoft Quantum Research Group, I'm here to talk about a different quantum state for use in applications of quantum computing, and that's an anionic quantum state. So let's first remind ourselves about what we mean by fermions and bosons. At their core, the difference between fermions and bosons is a difference of the physics of exchange. So if I have two particles, shown here as little spirals, and I exchange them in space, then the wave function that describes those two particles can acquire a phase, theta, and that phase for fermions is pi, which means that the wave function changes sign under exchange. For bosons, that phase is 2 pi, or 0, and so now the wave function does not change sign, you get a +1. And so this sign changing, or lack thereof, is what underlies Bose-Einstein condensation and the Pauli exclusion principle and a host of other physics. But we're going to go one step further in this statistics of exchange. If we decide that we only live in 2 dimensions, which most of the systems I'm going to show you for the rest of my talk, for which that's true, if we do 2 exchanges, so swap bottom with top, top with bottom, and do it again, I hope you can see that this is actually equivalent to taking one little swirly particle and wrapping it around the other. And mathematically, this is actually just called a braiding operation. So this would not be a very interesting thing to do in 3 dimensions because you could actually just continuously deform that path to the point where they had not actually traveled around each other. But nonetheless, in 2 dimensions, we have one particle wrapping around each other. And I hope you can see that you would just acquire twice the phase of the simple particle exchange above. So in the case of fermions and bosons, that 2 theta phase just gives you a +1, and you have no change of your wave function. But now I'm going to show you an experiment that some of my colleagues and collaborators in Purdue published last year. And this is with a two-dimensional electron gas and gallium arsenide. So that's the blue region in this figure here. And importantly, they applied an external magnetic field, which put this two-dimensional electron gas in a fractional quantum Hall state. And in a fractional quantum Hall state, the bulk purple area is insulating and the edges are now conducting. And the edges here are defined by these golden gates that are depleting the electron gas underneath. And they built themselves a small Fabry-Perot interferometer. And so you can see that at these sort of pinch-off points, they built a sort of quantum point contact. And the current that flows around the edges, some of it can backscatter and some of it can go through. And if you follow the path that the current takes, then you see that some current can travel all the way around and encircle this area inside the interferometer, whereas some of the paths do not encircle the area. Now, some localized defects or disordered potentials inside this region can mean that particles become trapped and localized inside this region of the interferometer. So interestingly, what they then did was they varied the applied magnetic field and they changed some local electric fields using a gate voltage. And they see these large interference effects, these oscillations from red to blue in the conductance. Now, this is maybe not that surprising. This is the Aharonov-Bohm effect. And it has to do with the area that's encircled and the field. What's more interesting are these little phase slips that they observed. And these are not just noise, because actually if they swept the field up from low to high field and they swept back down, they would trip over the same phase slip. So this phase slip, it turns out, is occurring when the field conditions are sufficient that they actually kick out a trapped particle. So what that's doing is it's changing the number of particles inside the braid. So what happens when you change the number of particles inside the braid? Well, you actually measure the statistics of exchange for these particles. And in fact, the phase slips, if you go and quantify them, were neither pi nor 2 pi nor 0. They were 1/3 of 2 pi. Now, if you've done your fractional quantum Hall effect homework, then you're familiar with this indicating that, in fact, the particles that are contributing to conduction are actually quasiparticles, and they're anyons. They're anyons that obey neither fermionic nor bosonic statistics, and the prediction of 1/3 of 2 pi for a phase slip is exactly what you would expect in this case of the 1/3 fractional quantum Hall effect. So why are anyons interesting for quantum computing? Well, that's because for some anyons, in addition to this interesting statistics of exchange, they have another property, which is that non-abelian anyons have braiding operations that do not commute. So what do we mean by that? We mean that if you have 3 such anyons and you perform one braiding operation on a pair, followed by another braiding operation on a different pair, the order matters. That is, this braid on the left is not the same as this braid on the right. And what that means is these braiding operations can now be used to encode quantum information in ensembles of these anyons, not by necessarily bringing the anyons close together and then allowing them to interact via some dipole or other interaction, but instead by just moving them around each other in space. So non-abelian anyons, for the sake of simplicity in this talk, arise when there is some degeneracy in the ground state of the system. And a braid, if you were to want to build a large circuit of these anyons for use in a quantum computer, what a braid could look like is something like what I show in the middle. So imagine we have a wire kind of in a T shape, and we have these little red dots. These are our anyons up here. If I want to braid anyon number 1 around anyon number 2, then what I can do is bring it down to this lower branch. I can bring anyon number 2 across to replace anyon number 1, and then I can bring anyon number 1 up to replace anyon number 2. And so throughout this process, I didn't bring them close together to interact. In fact, I kept them relatively far apart, but I nonetheless achieved the topological braiding operation that I needed. Now, I'll note for the experts that this kind of operation, which is actually at the heart of building a topological quantum computer, is also possible not with braiding, but with projective measurements of the parity, in this case, of the anyons. So if I had two of these wires, and I had these anyons at the end of each wire, I could put some sort of quantum probe between the wires. Here, schematically, we've drawn a quantum dot. And now if that dot does a joint measurement of anyon 2 and anyon 3, it can project the entire state into a well-defined quantum state. And it turns out that actually all of the operations in a topological quantum computer can be performed by this measurement-only quantum computing. And it's very similar to the projective measurements that are used in some quantum teleportation schemes that some of the groups here at Berkeley may be familiar with. So this is the kind of quantum computing that we at Microsoft are very interested in doing. It looks very different from some of the other quantum computers you may be familiar with. And so then the next step is to say, well, this is all well and good. That would be nice if you could just braid things to build a quantum computer. But how do you get non-abelian anyons to begin with? So in 2001, Alexei Kitaev proposed a simple model, simple to explain at the very least, of how to get non-abelian anyons in a physical system. Now, to start, he requested that we find a 1D chain of spinless fermions with superconductivity. So let's leave aside the scary part about finding spinless fermions for now. And let's just start with what that would mean, a 1D chain of fermions subject to superconductivity. So the picture here that he's drawn is a tight binding model. Each site in the lattice, the one-dimensional lattice, is an oval. And so at each site, I can define a fermionic creation and annihilation operator, A and A dagger. One creates, one annihilates fermion at each site. Now, I'm going to do a little math trick. I'm going to decompose these creation and annihilation operators into additional operators C1 and C2. So if you solve these equations for C1 and C2, you find that C1 and C2 can both be described as equal weight superpositions of the creation and annihilation of a fermion. They're like half fermions, fractional fermions. So not necessarily a realistic particle per se, in fact, more like a quasiparticle. So what's also interesting is that if you take what you know about fermions, which is that they obey anti-commutativity relations, then you can apply that to these equations, and you can find that those anti-commutation relations only hold true if the C1 operator is equal to C1 dagger, is equal to its conjugate, and similarly for C2. So when are operators equal to their conjugate? Well, only when a particle is equal to its own antiparticle. So I've now done some math tricks to end up with a particle that is its own antiparticle, which is the definition of a Majorana particle. Now, this is actually a Majorana quasiparticle, as I said before, because this is only a fraction of a fermion. And this all might not be very interesting if the world only contains cases like what you see on the left, where every one of these Majorana quasiparticles is paired with the other Majorana quasiparticle on its site. And the two of them just combine to form either a fermion or a hole, a lack of a fermion. And then what you get is a one-dimensional superconductor. There's a unique ground state to it. All excitations are gapped from this ground state, and it's not very interesting. But imagine a situation where you could end up with some of the Majoranas pairing with their neighbor on the next site over. So if that happens, then because this is a one-dimensional finite chain, you've got some unpaired Majoranas on one end and the other. And now the ground state of your system is superconducting in the bulk through along the length of your wire. And on the ends, you have these single states on each end, and they're actually pinned to zero energy by the particle hole symmetry of the superconductor. And the ground state now has a double degeneracy due to these quasiparticles on each end. You've actually set yourself up for all the ingredients necessary for non-abelian anyons. These excitations on the end are furthermore protected by the fact that the bulk of the chain is gapped. So what Kitaev was telling us is, if you can find yourself a topological superconductor in one dimension, which you can make out of, for example, a chain of spinless fermions, then you'll have yourself some Majorana quasiparticles and you can make yourself a quantum computer. And so for the rest of my talk, I'm going to tell you about our attempts to do just that. So how does one build a one-dimensional topological superconductor when one does not have spinless fermions at our disposal in the lab? What are some of the considerations for checking on the material's properties on the way to building one of these? And I promise to describe a lot of the bits and pieces in these legends along the way. And I'll call this a practical recipe, not necessarily because it's easy, but because I can dream it up more easily than I can a one-dimensional chain of spinless fermions. So when we are assembling quantum systems, actually, historically, we haven't always dove right into multi-qubit entanglement. In fact, precursors of a lot of our demonstrations of the manipulation of quantum states include convincing ourselves that we have all of the right ingredients. So from the same Nobel Prize winning research groups come demonstrations of quantum jumps, if we go back in time. On the left, you see the quantum jumps of fluorescence measured from an ion as it moved back and forth between the computational subspace and another state. And similarly, from those microwave cavities, there are jumps in the photon number in the microwave cavity that are probed by atoms transiting that cavity. And sometimes the photon number would even jump up. It wasn't controlled, but it nonetheless indicated the presence of quantumness and the ingredients necessary to build the controlled quantum systems. So let's talk about the ingredients for Majorana quasiparticles in what I've called a practical topological superconductor. So the first thing we want is something that looks like spinless fermions. So how do we get that? One solution is to find a system in which you have relatively strong spin-orbit coupling. So we have various semiconductors, particularly some of the heavy element 3,5 materials like indium arsenide and indium antimonide. And that's what I've drawn here. I haven't drawn it. What we've shown here in gray is a one-dimensional semiconducting nanowire. Strong spin-orbit coupling will give a momentum-dependent shift to an energy spectrum. And now, if in addition to strong spin-orbit coupling, we apply an external magnetic field orthogonal to the spin-orbit coupling field, so here in blue is the orientation of the magnetic field in this problem, then we lift a gap at zero momentum in the energy spectrum. And so then if we tune the chemical potential of the system so that it lies inside this gap, which we can do by applying electric fields with, say, local gate electrodes, then we find that we have an effective single band model. And so an effective single band model looks a little bit like a spinless model. Now, finally, we need superconductivity to get the elements of our one-dimensional chain of spinless fermions. And so we can introduce superconductivity by taking advantage of the proximity effect. We can bring in a relatively boring traditional superconductor, like the purple here is meant to show an aluminum layer that we've placed on our nanowire. And the proximity effect is what allows a superconductor in proximity to some other material to introduce superconductivity into that material. So what you end up getting is Cooper pairs in the semiconducting nanowire. And now you have a pairing gap that opens up on either side here at the Fermi points. And so in the presence of all of these ingredients, we establish a phase diagram like the one shown here, where for many points in phase space, we have a trivial superconducting phase. This is very akin to, in the Kitaev model I showed, all of the pairing of Majoranas happening on their individual sites. But by tuning the Xamon energy and the chemical potential, we can actually observe that there is a topological transition into a topological phase where now we expect those unpaired Majoranas at the ends of the wires. And that's what these little pink ghosts are supposed to be in here, where the end of the wire is where the end of the proximity effect is, where the superconductivity stops, even though the semiconducting nanowire continues. So I'm going to briefly mention a couple of the experimental techniques we use to check those ingredients along the way to make sure we've got the spin orbit coupling, the appropriate applied magnetic field, the induced superconductivity. So for example, spin orbit coupling, how do we check that we have the expected spin orbit coupling? Because it's both a materials property and crucially, it is derived from the geometry of the system. So we can use a property known as weak anti-localization to probe spin orbit coupling. In diffusive materials, as electrons bounce off of defects, sometimes they can take paths that enclose loops and return to a point along the wire here. And those paths, the multiple paths, can interfere constructively and so localize the electrons. So localized electrons will contribute to an increase in resistance along the wire. However, in the presence of spin orbit coupling, there is a path-dependent rotation of the spin, and that ends up resulting in destructive interference, and so reducing the localization and reducing the resistance. And so at its heart, what we're measuring is just the resistance along the wire, but in doing so, we're able to back out the strength of the spin orbit effect. And so this is a method that we use to check that, in fact, we have the correct spin orbit energy to achieve the topological condition. Another of the ingredients, the induced superconductivity, is important to check because it's not enough just to lay down some superconductor on top of your semiconductor and hope for the best. In fact, the proximity effect and the strength of the induced superconductivity depends a lot on the quality of the interface between the superconductor, here's aluminum, and the semiconductor, indium arsenide. And this is a really nice example of the epitaxial growth of aluminum on indium arsenide. And so in this plot here of tunneling spectroscopy, which I'll describe a bit more later, we see a superconducting gap. So that's the space between these peaks in conductance. And the superconducting gap, and this is a gap in the indium arsenide. This is telling you the indium arsenide is in fact superconducting. The quality of that gap, both the size and the depth, depends on how the aluminum was laid down, whether through epitaxial growth or through evaporative deposition. So this is the kind of measurement that we do to check on the quality of our materials interfaces. And finally, the third ingredient that I said is the Xamon energy. So the Xamon energy is what you're using to tune along the x-axis in this phase diagram. And for the geometries that we're using in Microsoft to try to develop these Majorana quasiparticle conditions, we need to apply relatively strong magnetic fields along the wires. So you see here in this schematic, B is down the bore of the wire. And a way we can measure the strength of the Xamon energy, which is proportional to the Landé G factor in the material, is we look again at that superconducting gap. So now I've oriented it along the y-axis here. So you see this gap, and we see the gap close as we increase the magnetic field. So these dashed lines are guides to your eye of how the gap is closing. And so the rate of gap closing in field can be used to back out the Landé G factor and therefore the Xamon energy. So this is very useful to give us a sense for how we can map external fields to our place in this phase diagram. So the last two examples I gave you of measuring both the induced gap and the Xamon energy were examples of measuring superconducting gaps to learn more about your system. And so I want to go into more detail about this, in part because it's a lot of what I do, but also because it's going to be crucial for what is really the message of my talk today, which is that measuring gaps, and in fact measuring gap closings, is the best method we can think of right now for really mapping out the topological phase diagram of our systems. So let me return to that phase diagram. As I said before, there's a trivial phase. It's where every Majorana is paired with its neighbor on one of these sites in the Kitaev chain. There's a topological phase where we expect unpaired Majoranas at each end of the wire. And crucially, along this boundary between the two phases, along this topological phase transition, we actually expect that the system is gapless, that the entire chain is gapless. And so observing a gapless boundary is going to be a very useful waypoint on this map to help us understand where we are in phase space. Now, there are previous examples of using the closing of a gap to identify topological phase transitions. This is an example from a group in ETH Zurich who built a honeycomb lattice for ultra-cold fermions. And they, in varying the potentials at the different lattice sites and applying modulations to those traps, they were able to realize the topological Haldane model. So the Haldane model is characterized by a topological phase transition between regions where the Chern number is 0, so that's sort of outside of this shape, and where it's plus or minus 1. And that phase transition occurs at a point where, or actually along this whole contour, where the gapped band spectrum closes at a single Dirac point. So the gap closes right here, for example, at this point. And so this group was able to probe that topological phase boundary by measuring the relative populations in the lower and upper band, or actually by measuring the transfer of populations. This transfer should only happen if the gap is closed. And so that's exactly what they show here, that there's a maximum transfer occurring exactly at the point in phase space where the gap closes. So this is very similar to what we want to do in our systems. We want to measure a gap closing in order to tell us that we've transited a topological phase transition. Our method for measuring a gap closing is going to be tunnel junction spectroscopy. I've already shown you a couple examples of this, but because it's going to be crucial to our understanding of whether or not we've convinced ourselves of observing a gap closing, I want to be careful about my definitions here. Tunnel junction spectroscopy is a relatively well-known tool in the condensed matter physics toolbox. When you have a barrier between two materials, you can measure the tunneling across that barrier. And it turns out that the tunneling with spectrum will be influenced by a couple things. It'll be influenced by the transparency of the barrier, but also by the density of states on either side of the barrier. So if one side of the barrier is a normal metal, a relatively boring density of states, Fermi-Dirac distribution, but for the purpose of this, we'll just say it's a relatively uniform distribution up to the Fermi level. And on the other side of the barrier, if we have a superconductor, well, we've got something more interesting going on. We have something like a BCS density of states where there should be a gap for which no conductance happens. And then above that gap, we expect a peak in the density of states at the gap edge. And so if we apply a voltage across this junction, then we can actually tune the relative Fermi levels on one side or another and probe the different points in energy of the density of states of the superconductor. And so that's exactly what I was showing you earlier with this induced gap measurement. So now we're probing the density of states of this proximatized, this superconducting semiconductor. And what we expect is some gap that's somewhere between 0 and the parent gap of the aluminum. And that's indeed why we see that the gap can differ depending on the deposition process of the aluminum. And it's an important metric for us to tell us how well we're doing at introducing the proximity effect. Another important note, particularly for systems where you're suspicious that Majorana quasiparticles might be lurking, is that this junction spectroscopy should be sensitive to the presence of zero energy states. So I'll remind you that these Majorana quasiparticles that we predicted should be pinned to zero energy because of particle-hole symmetry. So simulations predict that what we should see is not only a gap in the density of states, but also when we're in the topological regime, a peak at around zero bias in the spectrum. So that's something we can look for example, at the ends of wires. We can attach a tunnel junction and look for a peak at zero bias to tell us that there should be Majoranas present. Now let me return to how we can use this technique to map out the phase diagram of our system. So if I decide that I want to cross the topological phase transition by taking a horizontal path here that I've shown with these dots, then I expect in the trivial phase a gapped superconductor, a relatively boring one. But as I get close to the topological phase transition, that gap should close, because if you recall, it's supposed to be a gapless boundary between these two phases. And so in fact, I should see the gap closing in my spectroscopy. And finally, on the other side of the phase transition in the topological phase, what I hope to see is a gap open again. And now that gap has within it a small zero bias feature that indicates to me the presence of some bound particle at zero energy that is hopefully a Majorana quasiparticle. And so this is a simulation showing exactly that. So if you tune the Xamon energy, the expectation is there's a gap observed in tunneling spectroscopy. It closes at the phase transition here, and then it reopens very faintly. And at zero energy, there's a very well-defined peak in conductance indicating the presence of a Majorana. So here's the problem. All of these cartoons are well and good because they behave very well because I made them behave very well. But when we're measuring something that we think is a gap that is closed, like at the gapless boundary of our phase transition, or we're measuring something that we hope is a Majorana, but is in fact some blip in our spectroscopy at zero, how can we be sure that these are the states we expect and not just some local disorder in our density of states near this tunnel junction that is clouding our view of the entire bulk of our wire? And so I'll begin with this schematic of our wires that we measure and show you that all of these spectra that I've showed you so far are local conductance measurements of one end of the wire. So we're applying a voltage on this normal lead relative to our superconductor, actually, that we've grounded, and we're measuring tunneling through a barrier that's defined right about here. So this is telling us about the physics going on this end of the wire. But importantly, for the topological phase, what we expect is that it extends the entire length of the wire, as in the Kitaev model, where the entire chain was in a topological superconducting phase that allowed for unpaired Majoranas at distant ends. And those unpaired Majoranas are now in some very long distance, non-local entangled state, which is important for our quantum computation. And so, of course, these measurements are now prone to any of the disorder that is present on this local single side of the device. But perhaps you can see through my shaded box here and see where we're going with this. We can choose to do non-local conductance measurements. So this is a new technique that's been developed in the last couple of years, but it's relatively simple. Instead of modulating the voltage on one junction and measuring the current that results, we can modulate the voltage on one side of a two-junction device and measure the current on the other side and vice versa. And now what's interesting about doing this is that if you modulate the voltage on one side on the left side, say, and measure the current on the right side, then you only expect current to flow through the lowest continuous energy state that spans the entire wire. Now, this is making a couple assumptions about a lack of relaxation, but it's a useful and mostly true assumption to make. And so if we simulate what we might expect in the case of a topological phase transition observed through such a wire, where again, we're measuring the change, here we go, the change in current on the right side with respect to change in voltage on the left side, then what you see is a gap again. And now you can interpret this gap not as some disordered gap locally, but as a gap, the smallest gap that extends the entire length of the wire. And that gap closing should now indicate to you a bulk gap closing of the entire wire. And reopening should equivalently tell you what's happening along the entire wire as well. Now with two junctions and two voltages and two currents, your conductance is now a 2x2 matrix. You have the change in current on each side with respect to the change in voltage on each side. And so these again are simulations, but they're showing you that we expect to see in local conductance on the diagonals a gap that closes, followed by the presence of some local zero energy feature on each side. And in non-local conductance, we also expect to see a gap that closes. So again, this is the gap spanning the entire wire, but no zero bias feature appearing in non-local conductance, because these Majorana quasiparticles are localized to ends of the wire. So to go back to our attempt to map a topological phase transition as we go from the trivial to the topological phase, what we propose to do is to actually map the entire conductance matrix of these wires. And in doing so, observe that we can convince ourselves that we've entered the topological phase if we see two things. If we see a closing of the bulk gap at the phase transition, and we'll really convince ourselves that we've seen that closing if we see it in this non-local full wire length spectroscopy. And then we need to see in the topological phase the presence of these zero bias peaks on both sides of the wire, because there can be other effects that lead to additional conductance at zero bias, but there's stronger evidence for the presence of Majorana quasiparticles if they simultaneously occur on both sides. All of this has been simulated data so far, so let me show you some experimental data from some of my colleagues in Denmark, where they measured these conductance matrices and observed that as the gap is shown to close locally, so is the gap shown to close non-locally. And there are some additional considerations and demonstrations of local disorder not influencing the non-local conductance measurements that you may be interested in checking out. So to recap, what I'm proposing is that in order to convince ourselves of topological phase transition, we should take a page out of the work from the Zurich group with the Haldane model, and we should map the closing of a gap. And in doing so, following this red line in these phase diagrams here, which is exactly the increasing magnetic field in this simulation, we expect to see a boundary of the topological phase that is gapless, followed by the presence of not one, but two zero bias peaks in our spectrum. And this will give us very strong evidence that we've entered the topological phase, and we can furthermore map more of the phase diagram to give us stronger evidence. Now, this is beyond the time I have for today, but there are several other things that you can do to corroborate this evidence that you've entered this topological superconducting phase with your system. There is an expectation that at the topological phase transition, there should be a peak in thermal conductance. So superconductors don't typically demonstrate thermal conductance, but at this phase transition, this red line here, prediction shows you that not only should thermal conductance peak, but it should be quantized. Additionally, shot noise power should indicate the presence of a topological phase transition. And there are some suggestions that coupling these Majorana quasiparticle ends of wires to other quantum probes like quantum dots can indicate the presence or possibly the overlap of Majorana modes. And finally, I would say that the two strongest pieces of corroborating evidence for the presence of Majoranas and the existence of this topological phase would be to then take those Majoranas and either fuse them or braid them. This would really be the most compelling evidence of having built a not just observable but manipulatable quantum system. So let me just recap now. I hope that I've shown you that the discrete jumps that tell us that we have some of the ingredients necessary for building our quantum state are things like the induced superconductivity that we have to check and tweak up and improve in our materials. And we seek robust phases for building quantum systems, and a really compelling piece of evidence for a robust phase, the topological phase, is this observation of a gapless boundary followed by the presence of experimental evidence for Majorana quasiparticles like zero bias peaks. And finally, looking forward, having established this robust phase, we expect to be able to demonstrate control of these systems by performing either braiding or projective measurements to show that we can manipulate the Majoranas for building quantum computers. I have a lot of people that I can acknowledge at Microsoft. We have a very large and wonderful group, but I'll focus particularly on some of the people I work closely with in Redmond. And I'll also acknowledge that Microsoft has given me perhaps my most embarrassing photo to date. So here's me on my first day of work at Microsoft with Clippy. And some of you in the audience may actually be too young to have ever dealt with Clippy, but I can assure you he's the favorite of many of us. And I want to thank you so much for your attention and welcome any questions.
Thanks, Sydney. Everybody's clapping, but very silently and mutedly. Everybody, I welcome questions in the chat. If you really have a burning need to ask your question in your own voice, then just please raise your hand and I can call on you when we get to it. So let me start off with a question that was posed by Sajant Anand, who is asking about this construction you have for how to split a fermion into several quasiparticles and then try to place them in different locations. So does this same idea work for getting any kind of fractionalized quasiparticle? So can I decompose a site not into two, but maybe 3 or 4 or more quasiparticles just by the same sort of mathematical tricks?
The example of the fractional quantum Hall state that I showed can in fact be understood. The fact that they were 1/3 of 2 pi phase slips, you can understand that as quasiparticles that are 1/3 of an electron, if you will. So if you study your fractional quantum Hall effect, you'll see that you can decompose those carriers into different kinds of fractions. And I think the fractional quantum Hall effect is a useful construction for this because there's all sorts of fractions that are identified there. And some of those fractional quantum Hall states are good candidates for non-abelian anyons. And so that's definitely a topic of at least theoretical interest, if not yet experimental application.
Okay, I'll ask you another question. There's another question, but I'll get to it in a second. How does the transverse size of this one-dimensional wire affect the realization of Majorana quasiparticles? You portrayed everything as really a one-dimensional line, but of course your wires are some finite size, and maybe there's some other energies that come in, and so to what extent is this really a 1D system versus maybe higher dimensional?
Yeah, that's a great point. I did the trick of assuming that one dimensionality is achieved so long as the transverse extent of your wave function is not much smaller than the transverse extent of your wire. So just to give you an order of magnitude understanding, most of these wires are order 100 nanometers wide. in practice, actually, what we don't really think we have is necessarily a single channel, one-dimensional conducting channel, one-dimensional chain. Often we can have more than one channel, and this does not necessarily mean that this construction is going to fail. In a perfect world, we would end up with a single channel, and we can in fact figure out ways to measure how many conducting paths we have. But it turns out that those aren't necessarily going to interfere with the topological phase transition.
Okay. Okay, so now some questions. So Ella Lachman asks, I guess in a talk delivered at the APS March meeting, does Sarma mentioned that artifacts of disorder could look like zero bias peaks, but are not necessarily Majorana quasiparticles. I think this is what you were getting at in your discussion. So could these disorder artifacts also show up in the complementary measurements that you mentioned, or do you feel like this is really a sort of a smoking gun approach to identifying the spatially separated Majorana modes?
I think they certainly can. I think the story of the development of topological quantum computation has been learning about the systems as we go. And that is exactly what happened with learning about the different implications of disorder for some of our local conductance measurements. The non-local conductance measurements are exactly that. They're an attempt to rule out the presence of disorder for describing this gap closing that we observe. However, there are certain mechanisms, and relaxation is one of the ones I mentioned, that could contribute to if not a false signal, then a blurry signal. And so this is something we need to watch out for. And this is one of the reasons why I listed all of that corroborating evidence at the end. So some of those bits of corroborating evidence predict certain quantized values in certain measurements. Others are just additional bits of information to start to add to an overwhelming sea of observations. But finally, the thing that would really be the smoking gun, in my opinion, is fusion or braiding, something that really could only happen if these were non-abelian anyons.
Maybe looking specifically, this is Bjorn Bierski asking about the data, I guess the recent data you showed from measurements out in Copenhagen, where it looks like the simultaneous gap closing in the local and non-local conductance is observed, but it's not so clear what the signature is of the reopening of the gap. Is that impression right, or is there an explanation you can offer?
So the gap should reopen. We expect the gap, particularly in the non-local conductance, to reopen if we've entered the topological phase. And so I would say that those data did not necessarily show that we had entered a topological phase, because the topological phase is gapped and should be gapped. So that was a good eye, yes.
Should there be an extended region before it's opened, or?
So this is not what I've seen in the simulations that have been produced for this. I think often when we see extended regions where the gap is closed, we interpret that as low energy states that are for some reason pinned down to zero energy, perhaps due to repulsion from other states. So this is often the interpretation we use, but it's still not well understood. But I think suffice it to say, we won't be satisfied unless we see a reopening of the gap, and it's expected to happen over a relatively small energy window in that phase diagram.
Rob Cook is asking a question, I think, about the when everything is working well, how you intend then to realize quantum computing. And so this is measurement-based quantum computing. So is the idea one would make projective measurements, and then this would conditional on the measurement that is probabilistically it would affect gates in the instrument?
Yeah, so my understanding, and I will have to beg your patience, because my understanding is somewhat limited on the application of measurement-based topological quantum computing, but it is a projective measurement-based system where there is some non-deterministic path that the qubits can take. So maybe somewhat similar to some of the examples you may have heard about in photon-based quantum computing. So that would be if this were a measurement only. However, one could also construct the quantum computer using braiding, or one can use a combination of measurement-based operations and braids. So these are all different options for different circuit designs.
I want to ask at least one more question. I want to bring you back to your time working on the Compass project. And, you know, the Compass project does a really fabulous job recruiting students into studying the physical sciences, majoring and perhaps in physics, and supporting them on their way through their studies. When we talk to students that are trying to decide whether or not to select a major within physical sciences and mathematics, we find that one of their biggest concerns is whether or not they can see a clear career path for them, you know, getting a BA in physics versus other degrees that seem to be more career-oriented and more applied. So now that you're at this stage in your career, do you have any comments to offer to undergrads that are trying to make this decision?
Absolutely. Yeah, thank you for that question, because this was a worry I had the whole time too. And something that I learned, and by the way, I learned it through calling a lot of physicists in industry. They were always happy to have a coffee chat with me. And I asked them, how did you get your job? And their recommendation was to find the other physicists. And there are a lot of us. And to talk to them. And they helped me a lot with learning what are the particularly special skills that people with a physics education bring. And those special skills are big picture planning, they're imagining solutions. Often you're the one in the room who's willing to drop everything and get up on the blackboard and sketch out a completely different solution to a problem. When I find other physicists in industry, they're usually very excited to hear that there's a physics major who might want to work with them, because that means they would have a buddy to do that kind of thinking with. So while a lot of companies don't advertise that they want to hire physicists, sometimes it's just that they don't know that they want to hire physicists. And so my recommendation to those students is to absolutely get a physics degree, and then to look for the alumni from the department who've gone off out into the industrial world and get them on the phone.
Awesome.
That's great. I have a question.
Yes, please.
I'm wondering about the, have you explored the crystal structure? I'm sure you have, between the epitaxial growth versus, what was the other growth form?
Versus the evaporative deposition.
Yes. What does it look like there when the two media merge?
Oh, that is
interesting.
Yeah.
Interesting.
It is very interesting. It is a huge effort. It's really led by a fellow named Peter Krogstrup in Copenhagen, and he pioneered this method of epitaxial deposition of aluminum on lattice mismatched materials. So this really shouldn't have worked so as well as it did, except at what he does. So thank you so much for the question.
Wait, do you have any pictures from that, or I guess not? Do you have any pictures of the crystal, or?
There are some wonderful pictures you can find if you look up Peter Krogstrup's papers.
Construct. Okay,
Yes,
thank you so much.
You're welcome.
Wonderful talk.
Thank you.
Great. So I think just in light of the time, we're going to wrap up here. Let me mention that next week's colloquium will be given by Monica Schleyer-Smith. So we'll get to hear more examples of topology and ultra-cold atoms. But let me now just take one more opportunity to thank Sydney for coming to visit us and give us a great lecture. So thank you very much.
Thank you so much for having me, Dan.
Marie, are you still on? I didn't let you ask your question, but I think you should have a chance to ask it. There you go.